Whoa, dude. Check out those killer equations. Sweet. Actually, for the next 18 minutes, I'm going to do the best I can to describe the beauty of particle physics without equations. It turns out there's a lot we can learn from coral. A coral is a very beautiful and unusual animal. Each coral head consists of thousands of individual polyps. These polyps are continually budding and branching into genetically identical neighbors. If we imagine this to be a hyper-intelligent coral, we can single out an individual and ask him a reasonable question. We can ask how exactly he got to be in this particular location compared to his neighbors. If it was just chance or destiny or what. Now, after admonishing us for turning the temperature up too high, he would tell us that our question was completely stupid. These corals can be kind of mean, you see, and I have surfing scars to prove that. But this polyp would continue and tell us that his neighbors were quite clearly identical copies of him, that he was in all these other locations as well, but experiencing them as separate individuals. For a coral, branching into different copies is the most natural thing in the world. Unlike us, a hyper-intelligent coral would be uniquely prepared to understand quantum mechanics. The mathematics of quantum mechanics very accurately describes how our universe works, and it tells us our reality is continually branching into different possibilities, just like a coral. It's a weird thing for us humans to wrap our minds around, since we only ever get to experience one possibility. This quantum weirdness was first described by Erwin Schrödinger and his cat. The cat likes this version better. In this setup, Schrödinger is in a box with a radioactive sample that, by the laws of quantum mechanics, branches into a state in which it is radiated and a state in which it is not. In the branch in which the sample radiates, it sets off a trigger that releases poison and Schrödinger is dead. But in the other branch of reality, he remains alive. These realities are experienced separately by each individual. As far as either can tell, the other one doesn't exist. This seems weird to us because each of us only experiences an individual existence, and we don't get to see other branches. It's as if each of us, like Schrödinger here, are a kind of coral, branching into different possibilities. The mathematics of quantum mechanics tells us this is how the world works at tiny scales. It can be summed up in a single sentence. Everything that can happen does. That's quantum mechanics. But this does not mean everything happens. The rest of physics is about describing what can happen and what can't. What physics tells us is that everything comes down to geometry and the interactions of elementary particles. And things can happen only if these interactions are perfectly balanced. Now I'll go ahead and describe how we know about these particles, what they are, and how this balance works. In this machine, a beam of protons and antiprotons are accelerated to near the speed of light and brought together in a collision, producing a burst of pure energy. This energy is immediately converted into a spray of subatomic particles, with detectors and computers used to figure out their properties. This enormous machine, the Large Hadron Collider at CERN in Geneva, it has a circumference of 17 miles, and when it's operating, draws 5 times as much power as the city of Monterey. We can't predict specifically what particles will be produced in any individual collision. Quantum mechanics tells us all possibilities are realized. But physics does tell us what particles can be produced. These particles must have just as much mass and energy as is carried in by the proton and antiproton. Any particles more massive than this energy limit aren't produced and remain invisible to us. This is why this new particle accelerator is so exciting. It's going to push this energy limit 7 times beyond what's ever been done before. So we're going to get to see some new particles very soon. But before talking about what we might see, let me describe the particles we already know of. There's a whole zoo of subatomic particles. Most of us are familiar with electrons. A lot of people in this room make a good living pushing them around. But the electron also has a neutral partner called the neutrino, with no electric charge and a very tiny mass. In contrast, the up and down quarks have very large masses and combine in threes to make the protons and neutrons inside atoms. All of these matter particles come in left and right-handed varieties and have antiparticle partners that carry opposite charges. These familiar particles also have less familiar second and third generations, which have the same charges as the first, but have much higher masses. So these matter particles all interact with the various force particles. The electromagnetic force interacts with electrically charged matter via particles called photons. There's also a very weak force called, rather unimaginatively, the weak force, that interacts only with left-handed matter. The strong force acts between quarks, which carry a different kind of charge called color charge, and come in 3 different varieties: red, green, and blue. You can blame Murray Gell-Mann for these names. They're his fault. Finally, there's the force of gravity, which interacts with matter via its mass and spin. The most important thing to understand here is that there's a different kind of charge associated with each of these forces. These 4 different forces interact with matter according to the corresponding charges that each particle has. A particle that hasn't been seen yet, but we're pretty sure exists, is the Higgs particle, which gives masses to all these other particles. The main purpose of the Large Hadron Collider is to see this Higgs particle, and we're almost certain it will. But the greatest mystery is what else we might see. And I'm going to show you one beautiful possibility towards the end of this talk. Now, if we count up all these different particles using their various spins and charges, there are 226. That's a lot of particles to keep track of. And it seems strange that nature would have so many elementary particles. But if we plot them out according to their charges, some beautiful patterns emerge. So the most familiar charge is electric charge. Electrons have an electric charge of -1, and quarks have electric charges in thirds. So when 2 up quarks and a down quark are combined to make a proton, it has a total electric charge of +1. These particles also have antiparticles, which have opposite charges. Now, it turns out that electric charge is actually the combination of 2 other charges, hypercharge and weak charge. If we spread out the hypercharge and weak charge and plot the charges of particles in this 2-dimensional charge space, the electric charge is where these particles sit along the vertical direction. The electromagnetic and weak forces interact with matter according to their hypercharge and weak charge, which make this pattern. This is called the Unified Electroweak Model, and was put together back in 1967. The reason most of us are only familiar with electric charge and not both of these is because of the Higgs particle.